All right, hi there, everybody. Welcome back. We are moving on with chemistry, and today we're talking about something called Lewis dot diagrams. And you've probably seen these previously, but we're just going to go into a little bit more detail. So, the thing that we've kind of been skipping past this whole time we've been talking about chemistry is that molecules are actual physical things, and that these molecules have actual 3D shapes. So they take up space, and the way that they take up space is going to be different depending on the molecule. So if you take a look at an example here, if you look at water, we know water is H2O, that's no big surprise. But you might not know that water always has this, what we call a bent shape. So there's two hydrogens here in white, and the red is our oxygen. For some reason, they don't just go in a perfect line. They're not linear. They have this bent shape. And we can see, actually, this simulation lets us show that if we wanted to add a bit of energy to our molecule, we could change the angle that it's going to have between the hydrogens, but it's going to come to rest at like this perfect 104.5. That's like the happy spot for that angle where it wants to be. So the question is kind of why? Why does why does H2O take this shape and not, for example, just be in a line? If we compare that to carbon dioxide is two oxygens and a carbon, obviously, and it goes in this perfectly straight 180-degree line. And again, we can change that angle by adding a bit of energy, but when it gets a chance to settle back down, it's going to settle back down in this perfectly linear shape. Now, this gets more and more complicated as we look to different molecules: SO2, xenon, the difluoride, boron, tetrafluoride. This is BF3, and it goes in this perfectly flat kind of shape with the fluorine sticking off in all direction. You compare that to CFL3, which decides to take this shape, kind of more like a T shape. So what we're going to try and explore here is what is it that's causing chlorine trifluoride to take this shape, whereas boron trifluoride takes this shape. And so basically, how can we figure out how can we predict what the 3D shapes of these molecules are just by looking at their electron arrangement? And so we saw, for example, the 3D shape of water is this. And we sometimes call that the bent shape. And we're going to draw our just all the different atoms that are involved. And then these lines, of course, represent our bonds. So just a reminder that those lines are the bonds. And we've talked about this before, but remember that a bond is it's always two electrons. So by that we mean hydrogens sharing one, oxygen sharing one. So to make a bond, we have to have two electrons total. If you compare that to carbon dioxide, we saw that carbon dioxide was this like linear shape, and it does have something to do with these double bonds, as you might suspect, but there's also other stuff going on there too. So in order to understand why molecules make these different shapes, we use these Lewis dot diagrams. And these, again, it's chemistry, so there's always exceptions. It doesn't work perfectly every time, but it's basically going to allow you to predict what the three-dimensional shape of a molecule will be just based on its chemical formula. And for many molecules, it's going to work quite well. Okay, so the first thing you're going to do, the steps. 3 steps? Let's call them 5. So the first thing you're going to do is you're going to determine the central atom. And that might not make a ton of sense right now, but if we go back to our previous examples, what I mean by central atom is in this case here, carbon was the central atom of CO2, and oxygen was the central atom of H2O. So we sort of know it's a central atom because it's on its own, and then we can create symmetry by putting oxygens on either side. So where possible, we're going to maximize symmetry, although we'll see that they're not always perfectly symmetrical. So we're going to sum up the valence electrons, just the valence electrons, for all the atoms to determine the total number of electrons that we have available. And these are going to be electrons for bonding or for creating what we call lone pairs. So we're going to use electrons to create bonds. Between pairs of electrons, between each pair of atoms, and a reminder that a bond is a pair of electrons. And then we're going to arrange the remaining electrons around the outer atoms first to satisfy the octet rule, which is for all those p-block elements, they want to have 8 valence electrons. Note, of course, for hydrogen, it's only a duet rule, so hydrogen only needs to have 2 electrons. And then, if the central atom does not have a complete octet, we're going to form double or triple bonds in order to satisfy the central atom. So we start with the central atom, we draw all the other atoms around the outside, we add in our electrons, and then at the very end, we look to see if we need to form double or triple bonds. I think that'll make more sense when we go through a few examples. So our first example here is Cl2O, so dichlorine monoxide. And so again, just by looking at this, to me, what makes sense as a central atom is going to be oxygen with chlorines on either side. That's my most symmetrical kind of setup. Now, we got to figure out how many electrons we've got to work with. Chlorine, there are 2 chlorines, and each chlorine has 7 valence electrons. And then oxygen, there's only one of them, but it has 6 valence electrons. So 2 times 7 is 14, plus 6 gives me 20 electrons total to work with. So the first step, I've got my arrangement, I'm good to go. My next step is to create bonds. So remember, each bond counts as 2 electrons. So I'm going to use 2 electrons to make a bond here, and 2 electrons to make a bond there. Okay, I've still got 16 more electrons to go. My next step is to fill in the outer atoms first with electrons. So I want them to have a full 8. So I'm going to put 1, 2, 3, 4, 5, 6 electrons around this chlorine. And note now this chlorine is full because it's got these 6 kind of lone electrons, but don't forget it's got the 2 electrons in the bond. So that's a total of 8 electrons around that chlorine. I'll do the same thing over here, 1, 2, 3, 4, 5, 6. And so now this chlorine is also happy. If I count them up, remember I can count them by pairs because each of these represent electron pairs. I've got 2, 4, 6, 8, 10, 12, 14. I've used 16 electrons, but remember I've got 20 total. Well, I need to put the 4 electrons somewhere, and look, oxygen isn't happy yet. It only has access to 2 bonds. And so I'm going to put the 4 electrons here on oxygen. And what this creates is a situation, if you look at this now, any of these individual atoms are happy, which is to say they have a full outer octet, a full 8 electrons in their valence shell. There's no need to make any double or triple bonds. This is the shape, this is the 3-dimensional shape of dichlorine monoxide. That's what it looks like. Okay, let's take a look at this next one here. CH4, something you know and love as methane. I'm going to just guess here, I've never seen it before, but I'm going to guess that carbon is the central atom. And what I've got then is I've got hydrogens, and I'm just going to arrange them symmetrically all around the outside. I'm next going to count up my electrons. So carbon has 4 electrons. Hydrogen, there are 4 of them, and each one has 1 electron. So 4 plus 4, that's a total of 8 electrons to work with. Okay, I'm going to come along, and now that I've got my atoms laid out, I'm going to form bonds between my central atom and all my outer atoms. So I'm going to put a bond here, 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 and here. Now, if you count this up, this is 2, 4, 6, 8. I've already used up all 8 electrons on my just on my bonding. But remember that hydrogen only needs 2 electrons, so each of these hydrogens is happy. And this carbon has access to 2, 4, 6, 8 electrons, and so it's happy as well. Okay, we're just going to keep on rolling on. The next one, we've got hydrogen cyanate here. And this is a situation where you might look at this and say, well, I'm not sure what the central atom is. And if it was ever a test or quiz or anything like that, I would point you in the direction of the central atom, so at least you know where to start. But as it turns out, we can use carbon as our central atom. So I'll put nitrogen on this side, and I'll put hydrogen on that side. And next up, I'm going to total up my electrons. So I've got 1 electron there, plus I got 4 electrons for my carbon, and then my nitrogen has 5 valence electrons. So I've got a total of 10 electrons. My next step is to bond everything to the central atom. So I'll put 1 bond here and 1 bond there. Now, just a quick check-in. I've only used 4 electrons. This hydrogen is totally happy. It's got its 2 electrons, so it is done. Nitrogen is not happy, carbon is not happy. The question is, what do we fill next? Do I fill up carbon or do I fill up nitrogen? And what I would recommend is always fill up the outer atoms first. Okay, so start with the outer atoms, leave the central atom alone for now. And so you can see that I've got 10 electrons total, so I could put 1, 2, 3, 4, 5, 6 electrons around nitrogen. And now nitrogen's happy because it's got access to a total of 8 electrons. But if you count them up, 2, 4, 6, 8, 10, I've used all 10 electrons. There are no more electrons available. And carbon is still kind of out in the cold here. Carbon doesn't have access to as many electrons as it would like. And so what happens here is carbon's like, hey, nitrogen, you seem to have lots of electrons. Tell you what, if we're going to make a stable molecule, you need to share. So these what we call a pair of electrons, or a lone pair of electrons, these actually come along here to form another bond. And in fact, that's not enough. Carbon still needs more electrons, so these are also going to come along here and form another bond. And so what we're going to see in the end is we've got hydrogen with a single bond to carbon, but we have a triple bond between the carbon and the nitrogen. Don't forget that there's still these electrons on the nitrogen, and these are really important, okay? You can't just, these electrons that are sitting there, we call them lone pairs. You can't just ignore them. They are actually going to become really important in terms of figuring out the structure of your molecule. So we still draw those, even if they're not bonds, even if they don't seem like they're super important. Okay, let's take a look at, it's a nitrogen monoxide ion. It's got a little +1 charge there. So I don't really have a central atom, I guess. You could make either one central atom, it doesn't matter, there isn't one. And so now I'm gonna figure out my electrons. So nitrogen has 5 electrons, and then oxygen has 4, sorry, take it back. Oxygen has 6 valence electrons. 6 valence electrons. But then what about this little +1 here? The fact that it's +1 means I've actually lost 1 electron. So I have to take away 1 electron from my total, because that's how I got my overall positive charge. So I'm only working with 5 + 6 - 1 is 10 electrons. That's all I've got to work with here. So I'm going to make my bond to start with. Okay, I'm good. And then I'm going to start to fill in my outer atoms with additional electrons. And you can see here, it doesn't really matter which one you think of as the central, which one you think as the outer. Maybe I'll fill up oxygen first. So I've got two electrons there in my bond, and then I'm going to go 1, 2, 3, 4, 5, 6. So I've used up 8 electrons total. Oxygen's super happy. Nitrogen, not so much. So I'm going to then add 2 more electrons. I'm going to add a lone pair to nitrogen, and that's 2, 4, 6, 8, 10. That's all the electrons I get. I can't add any more. So I have to figure out how I'm going to make nitrogen happy. And the way I'm going to do that is by forcing these lone pairs to make additional bonds. So nitrogen is going to, in order to have access to 8 electrons, I'm going to have to bond both of those in there. And then my finished result is going to be nitrogen triple bonded to oxygen with a lone pair on nitrogen and a lone pair on oxygen. And if I'm just being really precise, I should remind everyone that this whole thing has a +1 charge. So I would just do that by putting a little bracket around it with the +1 charge. Okay, we're just going to do one more, and then I've got a few exceptions for you because that's how chemistry works. Chemistry has rules that always work unless, of course, there's an exception. So CH2O, let's figure out what this thing is. Well, again, I'm deciding on my central atom, and since if you think back to your organic chemistry, maybe we can have carbon as our central atom. And then just to kind of have things as symmetrical as possible, I'm going to just set it up like this. So I've got my oxygen and my 2 hydrogens. If I'm totaling up the electrons, carbon has 4 electrons. Hydrogen, there's 2 of them, and they each have 1 electron. And then oxygen has 6 electrons, so that's a total of 12 electrons to work with. I've already placed my bonds here. I'll just put those in red. And so I've used 2, 4, 6 of my electrons up. Hydrogen's happy, this hydrogen's happy, oxygen not happy, so I'm going to start to fill up oxygen. And now oxygen's happy. I've used 2, 4, 6, 8, 10, 12. I've used up all of my electrons. Everything's happy except for carbon. And so what must happen here is one of these lone pairs on hydrogen is going to have to jump in here and form a bond. And so in the end, I'm going to have H bonded to C, bonded to H, with a double bond to the O. And don't forget that I would keep my lone pairs here on the oxygen. Those are going to matter. And so you can see here what we've created is we've created a little aldehyde, right? Okay, so those are the basics. And then now we're just going to see a few exceptions. And the exceptions include boron and then a couple of the P block elements that are, in some of the rows that are a little bit lower down. So we're going to see how that works. BH3, okay, I've got boron and I've got 3 hydrogens. And then I've got to total up my electrons. So boron has 3 electrons. And then hydrogen, there's 3 of them, and they each have 1 electron. So that's a total of 6 electrons to work with. Okay, I've got bond, bond, bond. And now you'd look at this and say, okay, all the hydrogens are happy. But boron's not happy because it only has access to 6 electrons. And the thing is, there are no more electrons to go around. There are none available. There's no lone pairs on these hydrogens because they only need 2. So there's no extra electrons here to create any sort of bond. And so this is our first exception, which is boron. Boron is okay not having 8 electrons in its 8 valence electrons. So boron is stable with 6 electrons. It's okay with that. It's still probably going to react when it gets a chance, but this will form a stable molecule for the time being. All right, the next up is sulfur hexafluoride. Sulfur hexafluoride is that funny gas that makes your voice go super low if you inhale it. And so sulfur hexafluoride, I'm going to draw, I guess I'll draw a sulfur, and then I'm just going to draw this as symmetrically as I can. I'm going to draw just fluorines everywhere. It's just teeming with fluorines. Okay, fluorines all over the place. And so my sulfur is going to have 6 electrons. There are 6 fluorines, and they each have 7 electrons. So 6 times 7, 42 plus 6, I got 48 electrons. I'm swimming in electrons. Okay, first thing, I'm going to bond, 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 bond. So I'm going to use up 12 electrons just creating bonds. And then now I'm going to fill in, the outer atoms first. So I'm going to make sure each of these fluorines has 6 additional electrons surrounding it. And my hand's going to get tired trying to do this. Blah. Okay. So it's a bit of a mess. But if you look at it, each of these fluorines has access to 8 electrons, so they're happy. There's 6 of them, and so I can total up. If I count up all these individual electrons, I've used up all 48. I am there. I've got 48 electrons. But what you might be asking yourself is, what the heck is going on with sulfur? Sulfur has access to 2, 4, 6, 8, 10, 12 electrons. And so the answer to this is, our P block elements, when you get down to lower rows, they're able to accept more than 8. So sulfur can actually have more than 8 valence electrons. And the reasons for this, they're a little bit murky, but basically it comes down to the fact that it's just a bigger atom, right? It's a bigger atom, and it has, for example, it has access to D block orbitals. And those D block orbitals, as we've seen in the past, they just kind of make everything a little bit more complicated. So the larger P block elements, because they have access to some d orbitals, they can actually create all kinds of more complex structures. And so if you see that, if I gave you something like F6 and you're going, well, that's impossible, it's not. You know that it actually can bind. Similarly here, if I have phosphorus pentachloride, so if I've got my phosphorus here, and then I'm going to just sort of spread around the chlorines as symmetrically as I can. Okay. Phosphorus has 5 valence electrons, And then I've got my chlorine. There are 5 of them, but they've each got access to 7 electrons. So that's 5 times 7 is 35, plus 5 is a total of 40 electrons to work with. I'm going to bind each of these chlorines to the phosphorus, and then I'm going to fill in with my additional electrons. So each of these chlorines needs 6 electrons in addition to their bond. And again, we can see this situation where I've got, my chlorines are all happy, they've all got 8 electrons. But phosphorus is doing this funny thing where it now has access to 10 electrons, but again, it is okay for the same reason that sulfur was. Phosphorus is a larger atom, and so it's able to accept more than 8 electrons. Okay, that's it for Lewis structures.